Stanford University.
Classical mechanics is basically a set of rules about what those laws of motion look like. It's a set of rules. In fact, there are two varieties of questions. The first question is, I'm not sure about the order of them, but let's take them first. The first kind of question is, what are the specific laws for particular kinds of system? Particular system could be a planet moving in the field of a heavy mass. That has its own particular laws. Those laws are different than an electrically charged particle moving in the field of a magnet. They're different than, there are specific laws of nature. Okay. Then there's a more general framework. What are the rules for the allowable laws? Are there rules for the allowable laws? What's the grand framework in which all of the various different specific laws are framed in? And it's really the second question which we're really interested in. The first question will provide us with illustrations of the principles that govern what the allowable laws of physics are. Okay, so I like to start, and I always do in these classes, with a very simple set of illustrations. Who can guess what my illustrations are going to be? Coins, right? Right, of course. That's because you've been here before. Coins. Let's take the very simplest system that I can think of, a coin. I don't have a coin. So, when I say a coin, I mean an abstract coin laid down on an abstract table. The only thing about the coin which is relevant to us is whether it's heads or tails. The coin has two states of being, two configurations, two values, however we want to call it, heads or tails. Right? So there are two states. This is our dynamical system. It's one coin, and it has two states, heads or tails. That's all there is to the world, to this very simplified world. Question? Of course, there's an even simpler world. We can even go back to a simpler world. It's a coin with only one side. Then it's even simpler. All it can be is that one state. Right? That's a little too simple. Nothing can happen. Nothing ever happens. So this is our world. What is an initial condition? An initial condition is it's either heads or tails. Now what about laws of motion? Now we're going to make up some laws of motion. The laws of motion, of course, for this coin that just sits here, the law of motion is very, very simple. Let's put two circles here. One stands for heads and one stands for tails. What is the law of motion of this particular coin sitting on this particular table? The answer is it stays the same. So if we imagine breaking up time into little successive intervals, this stroboscopic world of a discrete coin like that, then the only thing that happens is nothing happens. Heads goes to heads, tails goes to tails. Or we can draw a picture. Heads goes to heads. Starting with heads, we go back to heads. Tails goes to tails. That's really a very boring law of physics, but it's a very powerful law of physics in that it tells you, however you start, you know where you will be arbitrarily down the line in time, right? If you start with heads, the history of the world will be heads, 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 dot, 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 forever and ever. So this law may be very boring, but it's very powerful. Or if you start with tails, it's going to be tails, 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 as far as the eye can see. So that's an example of a dynamical system with a law of motion, where the law of motion is just an updating, but it's in this case very trivial. There's only really one other law of motion that you can imagine for this system. And what is it? It is that whatever it is at one instant, at the next instant of the stroboscopic light, it's the opposite. In the next instance, the opposite. We could write it this way. Heads goes to tails. Tails goes to heads. And we can make a picture of it. We could picture this law of motion by, again, arrows. An arrow from head to tails, which says that if you start at heads, the tail end of the arrow always means what you start with. The head end of the arrow means where you'll end up. And that would be this law of physics. Heads goes to tails, tails goes to heads, heads goes to tails. And the history now of the world would be, if you start with heads, you then go to tails. Then you go to heads, then you go to tails, dot, dot, dot. But if you start with tails, you go to heads, tails, heads. Still pretty boring, but a little more interesting than the original first law. We could write some mathematics for this. In fact, we can write an equation of motion. Let's invent a symbol, a variable, which takes two values. Let me call it sigma. Why do I call it sigma? It's because sigma is a traditional variable associated with two-valuedness in physics. It has to do with the spin of the electron, or spin of particles, but we don't need to know about that now. Sigma is a variable that is either equal to 1, let's say, or minus 1. 1 for heads, minus 1 for tails. All right, so we can, instead of calling this heads and tails, we can call it sigma equals 1 and sigma equals minus 1. All right, we now have the idea of a configuration space which is labeled by the two possible values of a certain variable. It's not as rich as the variables we will use, for example, positions of particles, values of fields, or all sorts of other things. But nevertheless, it's a mathematical symbol whose value tells you which of the configurations you're in. All right, let's take this first law of physics. The first law of physics, not the first law of physics, the first law that I wrote down, the previous law, that was heads goes to heads and tails goes to tails. Let me write that in a mathematical form. Oh, let's call time t, and in our stroboscopic world, t is an integer. T is 0, 1, 2, 3. It can also be minus 1, minus 2, minus 3. So in the stroboscopic world, time is discrete, and it takes on integer values. So let's see if we can write an equation for the most boring law in the world. What it says is that whatever sigma is at a given time, let's put that over here, sigma at time t, at the next instant, t plus 1, it will be equal to whatever it was at the instant t. This is just a law that says that the spin, or that the coin doesn't flip. It just stays the same. Whatever it is at one time, it will be the same at the neighboring time, at the next time. Okay? So that's the simple law, heads, 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 or tails, 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 tails. What about the other law? The one which says that the coin does flip between each successive flash of the stroboscope. That's easy. That just says sigma of t plus 1 is equal to minus sigma of t. If it starts at 1, then at the next instant it's minus 1. If it starts at 1, at the next instant it's the opposite. So there we've written down equations of motion for a very, very simple system. Notice that it is completely predictive, completely deterministic. There's no ambiguity about what happens arbitrarily far down the future. Now, of course, I could come in and grab the coin and do something with it and do something else with it. That would disturb it. In our language that we've set up now, that would be because the system was not closed. I intervened, and I was not part of the system. So for a closed system, laws of physics are completely deterministic in classical mechanics. Okay, now let's think about a more complicated system. More complicated system, not much more complicated. Instead of a coin. Let's take, what's the next case, friends? A die, half of a pair of dice. You know, I never knew until I started teaching this that the singular of dice was die. I really didn't. Somebody corrected me once. I guess I called it a dice. And somebody said, do you mean a die? And I guess I did. Okay, so we have a die. A die has 6 states. 1, 2, 3, 4, 5, 6. That's the only significance for our purposes today about the fact that it's a die, is that it has 6 states. Again, we could label the 6 states 1 through 6. Let's put them 1, 2, 3, 4, 5, 6. And these stand for the 6 different configurations of laying the die down on the table. Okay. That's an initial condition. An initial condition is a choice of one of these 6 configurations. Right? But what about a law of physics? What about a law of motion? An equation, not an equation. I'm not going to write an equation. It's a little bit too complicated. But what's a possible law of physics for this simple system? Well, a very simple law would be, I'll give you a very simple law. A simple law is nothing happens. Nothing happens. However you start, you stay the same way. To graph it, we would just graph it like this. Whatever you start with, it's what you get at the end. That's about as boring as the simple coin. Okay, a more interesting law would be that you cycle around this collection of configurations. For example, a possible law of physics would be 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, 6 goes back to 1. I'll leave it to you to try to write an equation for this, an equation of motion. It's not hard to do. I'll just leave it to you to do. Okay, but you can see what happens. The history of the world would now be, well, give me the starting point, 4. After that, the history of the world is 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, endlessly cycling around. And that would be the theory of this particular die with a particular equation or a particular law of evolution. Now we could write down other laws. Another law, and the simplest way to write them down is to graph them. Oh, again, notice that it's completely deterministic. Another law would be to cycle in the opposite direction. 2 goes to 1, 1 goes to 6, 6 goes to 5. Or we could do more complicated things. They're not really more complicated, they're just more complicated to draw. 1 goes to 2, 2 goes to 5, 5 goes to 3, 3 goes to 4, 4 goes to 6, and 6 goes to 1. Now, this law is logically equivalent to the one which just cycled around. It's just a relabeling. It's a relabeling of the states, but it's, again, one cycle. 1 to 2, 2 to 5, 5 to 3, 3 to 4, 4 to 6, 6 back to 1. If I were to just rearrange them, redraw them, then it would just look exactly the same as the original cycle. So this law would be, what should we call it, logically equivalent to one of the others. Okay, but let's think about some laws which would not be logically equivalent. Here's a law that's not logically equivalent. Again, six points. I won't bother labeling them with numbers. 1 goes to 2, 2 goes to 3, 3 goes back to 1. 4 goes to 5, 6 goes to 5, 5 goes to 4, 4 goes back to 6. Right? It's again completely deterministic. Wherever you begin, the future is laid out for you completely. If you start with 3, you go to 1, to 2, to 3, to 1, to 2, to 3. On the other hand, If you start with 4, you go to, whoops, if you go to 4, you go to 6, 6 to 5, 5 back to 4, and so forth. So it's, again, completely deterministic, but it's not logically equivalent to any of the previous ones. It now has 2 cycles, and if you're on one of the cycles, you will never get to the, I'm giving them a name now, cycles, okay? If you're on one of the cycles, you will never get to the other one. So it's not that there are 2 systems. There's one die, only one die, but with this particular law of physics, you're trapped on one cycle or the other cycle. There's a name for this kind of behavior. It's called having a conserved quantity. A conserved quantity is something non-trivial that you can label the system with, which doesn't change with time. For example, we could label this cycle up here cycle number 1 and assign it a value 1. This cycle down here we could label with a value 2, and then we would say that if you start with 1, the quantity 1, or the conserved quantity 1, you stay with 1 forever. If you stay with 2, if you start with 2, you stay with 2 forever. This is called a conserved quantity. In other words, a quantitative quantity, all quantities are quantitative, but a quantitative quantity which just doesn't change. It's conserved. Right? That's called a conservation law. So this cycle over here, the single cycle system, doesn't have a non-trivial conserved quantity. You pass through every one of the states. This has a conserved quantity. It's either 1, what did I say, 1 or 0? I don't remember what I assigned them, but I assigned them 2 different numbers, this one and this one. Or we can make up more complicated, or not necessarily more complicated, but other examples. All right, and this one, 1 goes to 1. If the die is at 1, the rule is it stays at 1. If it's at 2, it goes to 3, and if it's at 3, it goes back to 2. And if it's at 4, it goes to 5. If it's at 5, it goes to 6. If it's 6, it goes back to 1. I've changed my color coding. Sorry about that. All right, again, there are 3 cycles now. There are 3 cycles, and if you get onto any one of them, if you start on any one of them, you stay on it. You could describe this by saying the first cycle over here corresponds to the value 0, let's say. Corresponds to the conserved quantity having value 0. It could be 1 over here, and it could be 2 over here. If you start with a conserved quantity being 1, then it stays 1. If you start, what did I say? Sorry, 0. If I start with a conserved quantity being 0, it stays 0. If I start with it being 1, that doesn't tell me exactly where I start, either here or here, but it tells me I start with one of these 2, and I stay with that value. I don't change, I change the state, but I don't change the value of the conserved quantity. Likewise over here. So we can consider a variety of different, logically different evolutions. What is it that distinguishes them? Well, really it's just the number of cycles, the number of distinct cycles. This is a 3, well, no, it's a little more than that. It's a little more than that, but you can see, you can play around with this and investigate it, and you'll very quickly get the point if you haven't already gotten it. Any questions up till now? Yes, sir.
So, in the very first example, you brought up with the coins, where you have a progression, either TTT or HHH or HTHT.
Right.
So those, I mean, I can imagine other sequences of H's and T's.
Yeah.
But if I were to try to construct one of those, I think it would have to depend on more than just the preceding state, maybe several states backwards.
Not for that. Not for those laws.
HTT, HTT.
That's a different.
Right.
Right. You can. Right. That's right. You could invent laws where to know what happens next, you have to know not only the previous, but the second previous state. Right, that's correct.
Is that as important to what
Yes, yes, it will become important. It will become important. But under those circumstances, you would say that the state of the system is not characterized by just whether it's heads or tails. It's characterized by the configuration and the previous configuration. And so you would have, in that case, 4 configurations. The 4 configurations would be heads preceded by tails, heads preceded by heads, tails preceded, and then you would do exactly the same thing, except you would say there were 4 possible states. Right. So, and that of course is, I know exactly where you want me to go, but I'm not going to go there yet, but right, not yet. So it's what I said before. The state of a system, or the configuration, consists of all the things that you need to know to predict the future. So in the case that you described, what you need to do, what you need to know, the initial condition consists not only of what the coin is doing, but what it was last doing. Good. So that's a good point. And we will come back to it. All right, so we have the idea of configurations, we have the idea of isolated systems, we have the idea of conservation laws. Let's just point out that there's nothing to prevent us from considering systems that have infinite number of states. It doesn't have to have an infinite number of objects to have an infinite number of states. It just needs to have one object which can be rearranged in an infinite number of ways. For example, if we had an infinite line, and on that infinite line we marked off the integers, and we said there's a particle. What does a particle mean? A particle now just means a thing which occupies one of the places. The places now consist only of the integers. What's in between doesn't matter, doesn't count. All right. So a particle is simply an object which sits at one of the integers. Okay. You could have an infinite array like this, and then you would say the particle has an infinite number of states, namely the infinite number of possibilities of where it can be. We could label them by an integer, n. And then we could invent laws such as, wherever you are, move to the right 1 unit. Wherever you are, move to the right 1 unit, and that would be a picture that would look like this. It doesn't cycle. Nevertheless, we're going to call such a thing a cycle, but you can see it doesn't cycle. It just goes on and on forever and ever. We could have another law. The other law could be, wherever you are, jump 2 units ahead. Wherever you are, jump 2 units ahead. No, I think I'll do it this way. If you're over here, jump 2 units ahead. If you're over here, jump 2 units ahead. If you're over here, if you're over here, and so forth. All right, so we make a picture then of a kind of law of physics which tells us to jump 2 units ahead. Again, make up an equation for that. Make up an equation for that. It's easy to do. In the first case, there was no interesting conservation law. There was only one cycle, if you like. Wherever you are, you will always either get to any other point, or if you go back into the past, if you imagine running it back into the past, you will have come from that point. So there cannot be any interesting conserved quantity, because you'll pass through every single one of these integers, and so they can't be distinguished by a conserved quantity. In the second case, there is a conserved quantity, and you can call it the oddness or evenness of the position of the particle. You could give all odd numbers, represent them by a value of a quantity which is 0, and all even, that's weird, isn't it? Let's make the odd numbers have integer value 1, and the even numbers be labeled by integer value 0. And then you would say there's a conserved quantity which can either be 0 or 1. If it starts at one of them, it stays there. It starts at the other, it stays there. All right, so having an infinite number of configurations doesn't change the picture very much. It does open the possibility that there's a kind of endless evolution which never repeats itself. So in that sense, it gets a little more interesting. And you can think of all sorts of generalizations of this. All right, so I laid out some, I'll call them allowable laws of physics, or allowable rules. Let me talk now about some rules which are not allowable. No, not allowable by whom? By me. But of course, I'm simply reflecting the way real classical physics works when I say allowable and not allowable. Let me draw a picture of a non-allowable or an unallowed law. It's completely deterministic. It completely predicts the future, but there's something different about it than the laws that I've drawn over here. And I'm going to do it by drawing the picture for it. It's got, we can make up many, many examples, but for this particular example, it's got 3 states. So this is a 3-sided coin. A 3-sided coin, it's got heads, tails, and, I don't know, sides. Heads, tails. I was going to think something a little more risque, but tails is about as risque as we're going to get.
How about an edge?
Yeah, an edge. Sorry, edge. That's pretty edgy. Heads, tails, and edges. Okay. All right, here's a law of a kind which represents something that we will not allow in classical physics. Heads goes to tails, tails goes to edges, and edges goes back to tails. All right, now wherever you start, the history is completely predictive. If I start with tails, I go to edges. If I tails, edges, edge, tail, so it goes tails, edge, tails, edge, tails, edge, tails, edge. You just follow the lines. If you start at heads, you go to tails, then edge, then tails, then edge, then tails. So here's some histories. First of all, starting with heads, it's heads, tails, edges, tails, edges, tails, dot, dot, dot. If I start at tails, I get tails, edges, dot, dot, dot. If I start at edges, now what is it that's odd about this law? What's odd about this law is that it is completely predictive into the future, but it is not predictive into the past, so to speak. If you know that you're at tails, you don't know where you came from. Did you come from edges? Well, maybe. But you could have also come from heads. So while you can predict the future, you can't redict. What's the opposite of predict? Retrodict, that's the word I'm looking for. You can't retrodict the past from this law of motion. One configuration or several configurations run into the same configuration. And so you can't tell if you're over here whether you came from here or here. The word for this is that it's not reversible. Here's the way to think about it. Reverse every arrow. Now you have an unpredictive situation. If you're at tails, you don't know whether to go to heads or whether to go to edges. So it's a predictive situation one way, but not retrodictive the other way. The word for this is not reversible. I won't call it irreversible. That's a little too definite. It's not reversible. Okay. It can't, you can go one way, but not the other way. This is the kind of law that is not allowed in classical physics. Yes, sir. Oh, ma'am, I can't see.
Something like that be allowed if the probabilities were assigned to each possible outcome?
Well, okay, that of course depends on what you're trying to represent. Classical physics doesn't allow probability, so I think I could escape from the question by just saying we don't do that in classical physics. But we can imagine, of course, we can imagine anything we want. In fact, we can imagine this, and we can study its properties. The point is, in one way or another, it conflicts with the rules of classical mechanics. Probability, or let's call it non-deterministic laws, also conflict with the rules of classical mechanics. So it's a very good question, and it's something we'll want to come back to, whether when quantum mechanics, for example, which is not deterministic, does quantum mechanics have an analog of this reversibility idea, even though it's not deterministic? And the answer is yes, but not tonight.
Classical statistical mechanics.
Well, classical statistical mechanics also has, keep in mind that the rules of classical statistical mechanics begin with the laws of mechanics, okay? We begin by assuming, all right, let's talk a little bit about the limits on predictability for a moment. If we have a perfectly predictive system of equations, it won't allow us to be completely predictive if we don't know the initial conditions exactly. So we need to know two things to predict the future. One is what the rules are, the laws, and one is what the initial conditions are. Now, in these very, very simple systems, it's easy to imagine that we could know exactly what the initial conditions are. Of course, we may not. We may know that we begin with either, not this one, but this one. We may know that we begin either with edges or heads, we don't know which. And then there would be some ambiguity in what happens. Not ambiguity because the equations have ambiguity in them, but because our knowledge of the initial state is imperfect. Okay? This is easy to understand. For these simple discrete systems, it's easy to imagine that we can do enough experiment and very quickly just look at a coin and know the initial condition perfectly. In the real world, where we're faced with degrees of freedom which are continuous, meaning to say they can be any number on the continuous real axis, any number of numbers, the positions and velocities of all the particles in the world, you can never know them perfectly. No matter how many decimal points you may have that you may have measured, decimal places you may have measured about the location of a particle, you still don't know it exactly. So there is always a degree of ambiguity in your knowledge of the initial conditions. That degree of ambiguity may or may not sort of blow up in your face that small changes in what the initial conditions are may or may not give rise to large changes in what happens in the future. So the right way to say it is, if you knew, well, we have to be quantitative, but if you knew the initial conditions perfectly, then you could predict the future forever and ever in a true classical mechanical system, and you could also predict the past perfectly. If you have imperfect knowledge of the initial conditions, you want to quantify that. How imperfect is it? And if you can quantify it, it may allow you to answer the question, how long into the future can you predict things? So if you knew enough about the initial conditions of the atmosphere, you might be able to predict the weather for 3 days. But because your knowledge is limited, and because the atmosphere is one of these systems where little errors build up, they're called chaotic, because the atmosphere is chaotic, no matter how well you know the initial conditions, it is always true that if you wait long enough, you won't be able to predict the future. On the other hand, if you say, I want to be able to predict the future for X number of years, it should be possible to say how precisely you have to know the initial conditions. Okay, so when we come to the real world, this idea of predictability becomes a little more complicated. But I started on purpose with very simple discrete systems. Okay, so laws that are allowed, laws that are not allowed. The laws of classical mechanics are not only deterministic into the future, but they're deterministic into the past, which makes them reversible. Now, how do you look at one of these pictures and decide whether it's a legal law or not? Well, it's very simple. If every state has one outgoing and one incoming arrow, that means that you know where it came from and where it's going. So when you draw one of these pictures, if you want to know whether it is an allowable legal law in the sense that I've defined, I'm using legal now just as a term for reversible systems. If you want to know whether it's reversible, look at the arrows, and if each state has one incoming and only one incoming and one outgoing, only one outgoing, then it is both deterministic and reversible. There are analogs of all the things I'm telling you now about more complex systems and more interesting systems, such as particles moving around. Okay, so that's sort of warm-up preliminary about what classical mechanics is about. It's about predicting the future, or using the predictability, the fact that in principle you could predict the future in other ways, such as statistical ways, to limit what will happen. All right, now we want to move on to a more realistic world, and in fact the world of particles. We're going to be interested in the world of particles moving, and a particle for our purposes can be thought of as a point particle. If we want to make a more complicated system, we'll make systems of particles, points particles, but we'll consider point particles moving around in space. So what do we have to know? What are the configurations of a point particle? What do we need to know? Well, okay, before we do so, I think we should do a little bit of mathematical preliminary. I want to remind you, for those who don't know, or who knew but don't remember, or remember but just barely, what vectors are and what coordinate frames are. A coordinate system is just a way of describing space quantitatively. And incidentally, for our purposes today and largely in general, we will of course assume that space is three-dimensional. And so a point of space will be labeled by three coordinates. But we're perfectly free to think about systems which are higher dimensional or lower dimensional, and we will do so. Since we're interested in formulating the basic principles, we don't have to restrict ourselves to very, very specific examples. A particle could move in one dimension. It could move in 5 dimensions, and we will be interested in all the possibilities. But for the moment, let's just think of particles as things which move in 3 dimensions. All right. So in order to be quantitative about the location of particles, we introduce a coordinate system. Coordinate system, Cartesian coordinates will be the usual things we'll introduce. Later on, we'll introduce other ways of describing locations of particles. But for the moment, we take space, we identify an origin. The origin is up to us where we want to put it. I can put it over here, I can put it over here. It should be that the important questions that we're interested in should not depend on the convention of where we put the origin, but it's useful to fix it once and for all and say the origin of coordinates is located in Palo Alto, wherever we want to put it. Here it is. Then introduce axes. The axes are taken to be mutually perpendicular. You can check that they're perpendicular by with a t-square or whatever it is that you use to align axes. And you label them. We can label them x, y, and z. Or x1, x2, and x3. We'll use both kinds of notations. But there's also an ambiguity about the orientation of the axes. Given that they're mutually perpendicular, we still have to decide, I don't know how to draw it, I think you know what I mean, which directions they go in. And so that's like fixing the origin of coordinates. We also have to fix an orientation for the x and y axis. Once we fix the orientation for the x and y axis, the third one is fixed. It's perpendicular to it. Incidentally, there's a convention, and the convention is called a right-handed coordinate system. The convention is when you've picked x and y, you still need to know one discrete piece of information. Is z pointing out of the blackboard, or is it pointing into the blackboard? And we settle on that by a rule. It's a convention. It's arbitrary, the right-hand rule. If we take our thumb and our index finger, thumb along x, index finger along y, then z is the middle finger, the direction of the middle finger. Right. So that's the right-hand rule, and it selects out this coordinate system from the other one where z goes in the other direction. Okay, so that's the idea of a right-handed coordinate system. We also have to mark off distances along here. So distances are marked off equal distances with a ruler. And of course, in saying that we mark off distances, we're also assuming a set of units. The units could be meters, it could be inches, it could be feet, it could be light years. So again, another, not ambiguity, but another convention is to choose our units. But once we've chosen our units, we can lay off distances along here. And then every point in space can be labeled by a value of x, y, and z. Let's see, how do we draw this? It has a height, y. It has an x, and it has a z, z. If you like, you can think about how do you get to this point from the origin. You go a certain number of steps along x, you go a certain number of steps along y, and then you go a certain number of steps along z. And those quantities, x, y, and z, are the coordinates of the point. So a point is labeled by a set x, y, and z. Now, I know you all know this, but let's spell it out anyway. Okay, so that's the way we describe a point. That's the way we describe a particle. And of course, if we have a system of particles, many particles, then of course we just have to put in one such point for each particle. Okay, vectors. What is a vector? A vector is an object which has both length and direction. For example, a very simple vector is the position of this point relative to the origin. Here's the origin, and the position of this point relative to the origin has a magnitude, which is the distance from the origin, and it has a direction, namely just the direction of the arrow connecting the point with here. Think of that vector as an object which has a length and a direction, but don't think of it as being located anywhere. Think of it as being the same no matter where I draw it in space. In fact, I don't even have to think about drawing it in space. It is what it is. It's a magnitude and a direction in space. That's called a vector. And from now on, we will label vectors by putting a little bar on top of them. If I'm really conscientious, I'll put a little arrow on top of them. If I forget the top of the arrow or I get bored writing arrows, I'll just put a little bar on top. And here and there, I may even forget to put anything on top, but you'll remind me. Okay, so a vector has a magnitude. The magnitude is its length. It does not have to necessarily be a relative position. It could be a velocity, it could be an acceleration, something that, or other things. It could be an electric field, be all sorts of things. The criteria for it to be a vector is that it has a length and a direction. Okay, so that's the notion of a vector. Every vector can be described or has associated with it a length. Let's call the length of it. In fact, for the length of it, I don't have to put a vector sign. 2 bars on either side of it, the absolute value of it, are called its length. So this is a way of writing its length. Okay? So that's the length of the vector. And the vector, it's always positive or 0. It could be 0. If the vector has no length at all, in other words, if this point were right at the origin, it would have no length at all, it's always either positive or 0. So every vector has a length, and it has a direction, which is not so easy to write down. Okay. It can also be described by components. The components of the vector are exactly what I said before. If you wanted to go from the origin to this point over here, you would go a certain number of units of x, a certain number of units of y, and a certain number of units of z. The other way to define it is to drop a perpendicular from the point to each one of the axes. I don't draw this very well. Let's see, I think, how are we going to do this? I want to get this vector to be out of the blackboard. How can I get it to be out of the blackboard but draw it on the blackboard? Anytime I draw it on the blackboard, it always looks like it's on the blackboard. Okay. From here to here. Okay. We drop a perpendicular from the tip of the arrow to each one of the axes, and that lays off for us a distance along those axes, which are the 3 components of the vector. We'll call them Vx, Vy, and Vz. When I'm writing the components, I have no need to put the arrow on top of them. The components themselves are numbers. Okay. What is the length of this vector whose components are Vx, Vy, and Vz? Yeah, the square of the length is Vx squared plus Vy squared plus Vc squared. Pythagoras' theorem, except in 3 dimensions. I'll assume it, we won't prove it, that the length of V, the magnitude of V, is the square root of the sums of the components. That's the notion of the magnitude of a vector. And the direction of the vector is encoded in the ratios of the different components. For example, if the x component is much bigger than the y component, then the vector is pointed more or less along the x-axis and so forth. The components can be positive or negative. If they're negative, they're pointing along the negative axis and so forth. All right, but as I want to emphasize now, again, that the notion of a vector is not necessarily tied to the location of anything in space. It is what it is. It's a length or a magnitude and a direction. And if you move it around, it doesn't change the vector. That's just a mathematical definition of the way you think about vectors. You don't think of them as being tied to a point in space. You can. I mean, there are circumstances when you may want to tie a vector to a point of space. For example, you might want to ask, what is the electric field at a particular point of space? Then that vector is tied to that particular point in space. But the notion of a vector transcends that. It doesn't matter where you put it. All right, now we have to talk about the algebra of vectors. I really feel sorry for all of you people who've sat through this endless number of times before, but it's funny, there are some things, like a book, which no matter how good the book is, pretty much, except for some extremely special cases, you really only want to read it once. You know, you may say you want to read that book, you love that book so much you could read it endlessly, but it's not really true. You read it once. There are other things like a good piece of music, which you want to hear over and over, and It doesn't matter how many times you've heard it. It just is always good to hear. I assume my lectures are like that. What? Okay. All right, so let's talk about the algebra of vectors. The algebra of vectors, first of all, you can add them, you can subtract them, you can multiply them by numbers. So let's talk about that a little bit. Given a vector, let's call the vector A. Again, it's a length and it's a direction. You can multiply it by a number, an ordinary number. Not an integer, but a real number. Let's multiply it by the number c. What's the definition of that? It depends on whether c is positive or negative. If c is positive, it's a vector along the same direction, except its length is multiplied by c. So twice a vector means a vector of exactly the same direction, but twice as long, and so forth and so on. We can also define the negative of a vector. In other words, we could let c be minus 1. I can either put here minus 1 or just minus the vector. And of course, the negative of a vector is exactly the same vector except with a direction in the opposite direction. That's the definition of multiplying a vector by a number, by an ordinary number. Now you can also add vectors. Let's just remind ourselves about the rules for adding vectors. There are three ways of thinking about adding vectors. In the first way, let's say a plus b. We take a and we lay it out. Here's one end of it, the tail end of it, here's the arrow end of it. Then we take b and we put the tail of b at the head of a, and we draw a triangle. The triangle has its third leg, c, which is the sum of a plus b. It might be a degenerate triangle. It might be that b is along the same direction as a, in which case c will also be along the same direction. It'll look something like this, in which case it's a kind of degenerated triangle. But still, we'll just think of it as a triangle. We can add vectors by this rule. We can multiply vectors by numbers. Oh, before I do that, let's just talk about the two other ways of adding vectors. They're trivial. According to this rule, it looks like it might depend on which one I laid down first, but of course it doesn't. You can choose a rule which is symmetric between the two of them. If this is A and this is B, you put the tails of A and B down together, you draw a parallelogram, and you draw the diagonal of the parallelogram, and that's called C. And in this form, it's completely manifestly clear that it doesn't matter whether you put A down first or B down first. So A plus B is the same as B plus A. Okay, so that's vector addition. You can multiply vectors by numbers, either positive or negative. Let's call this A. We know exactly what that means. We can multiply B by a number B. What am I doing? B. And we can add them. We know how to multiply by numbers. We know how to add. And that means we know how to construct the vector A times vector A plus B times vector B. We know exactly what that means. Okay. The third way of adding vectors is to use the components. So if we have two vectors with components AX, AY, and AZ, and BX, BY, and BZ, then CX is just equal to AX plus BX, and likewise CY and CZ. We could summarize this all by saying C sub I, where I could be X, Y, or Z, or 1, 2, or 3, is equal to AI plus BI, and that's an equivalent way, a useful way to add vectors, since often we specify the vectors by their components. All right, if we can add vectors and subtract vectors and multiply them by numbers, the natural question is, can we multiply vectors Can we divide vectors? Well, no, we're not going to divide vectors. The idea of vector division is not a well-defined idea. But there are vector products. There are two kinds of vector products, two distinct concepts of multiplying vectors. In one of them, when we multiply two vectors, we don't get another vector, we get a number, a thing that's called a scalar. And sometimes a number is just called a scalar. So one definition of the product of two vectors is called the dot product. Let's talk about the dot product of two vectors, A dot B. A dot B is defined in the following way. You take A, you take B, and now you think of the component of A along the axis of B. What does that mean? That means you drop a perpendicular from the end of A to the axis, not to the x-axis, not to the y-axis, not to the z-axis, but to the axis defined by B. So you drop a perpendicular. And now you take the length of, let's call this here A sub B, the component of A along the B-axis. You take the component of A along the B-axis and you multiply it by the component of B along the B-axis. What's the component of B along the B-axis? It's the magnitude of B. All right? So you take the component of A along the B-axis, you multiply it by the component of B along the B-axis. All right? And that's called the dot product. I'll write it out in a minute more definitely. That's called the dot product. But the way I defined it, it looks like A dot B might not be the same as B dot A. After all, the rule for B dot A would be to drop a perpendicular from B onto the axis defined by A, which is a different thing, and then multiply them together. Is it obvious that A dot B and B dot A are the same thing? Well, if we can write them in a manner which is symmetric between the two of them, then we'll know they're the same thing. Okay, so let's call this angle here theta. The magnitude of A is the length of A. The magnitude of B is the length of B. What is the component of A along the B-axis? A sub B is equal to the magnitude of A times the cosine of the angle between them, right? Let's call it theta AB. Theta is an angle now, and it's the angle between A and B. That's the component of A along the B-axis. We now multiply that by the magnitude of B to get the dot product. All right, so the dot product is A dot B, and it's equal to A, B, cosine theta. I won't bother writing theta AB. It's A along the component of A along the B-axis, that's this, times the component of B along the B-axis, which is just the magnitude of B. It's AB, magnitude of AB, cosine of theta. Now in this form, it's completely clear that it's completely symmetric between A and B, and it doesn't matter in which order you multiply them together. The cosine of the angle is just the cosine of the angle. Is A dot B always positive? And under what circumstances, if not, under what circumstances would it be negative? If the cosine is negative, when is the cosine negative? The cosine is negative if the angle is bigger than 90 degrees. So that would be the situation, for example, where A was pointing like that. Then the component of A in the B direction would be negative. Cosine of theta would be negative. For an angle bigger than 90 degrees, the cosine is negative. What about two perpendicular vectors? 0. Cosine of theta is 0 for 90 degrees. So a diagnostic for deciding whether two vectors are perpendicular or not is to calculate their dot product. Now, that can be useful, and the reason it can be useful is because we can express the dot product in component form. If we express the dot product in component form, I won't prove this. This is not hard to prove. That in terms of the components of the vectors, this is equal to ax bx plus ay by plus az bz. In other words, you multiply the components and you add. That can be easily proved. A little bit of trigonometry, not much. That this is equal to this over here. Now that's nice. Let me show you how you can use that. Well, let's see, do we really need that? Well, if I just were to give you the components of A, 3 numbers, and the components of B, 3 numbers, and asked you to compute the angle between A and B, your first reaction might be to throw up your hands and say, well, I don't know, get me a protractor and I'll try to measure it. But here's a tool now. You calculate the dot product between them. That gives you A dot B. You can also calculate what is the magnitude of A. It is the dot product of A with itself. Let's write A, oh, sorry, that's not quite right. A dot A, what is that? That's just the square of the magnitude of A. So that's A squared. Likewise for B. So you could calculate the magnitude of A, or the square of it is ax squared plus ay squared plus az squared. Likewise for the magnitude of B, and then you would calculate the angle between them by calculating the dot product of the two of the vectors. So from the magnitude of each one of them and the dot product of 2 of them, you would compute the cosine of the angle between them. All right, so that's a good trick if you want to know the angle between 2 vectors. Let's prove the law of cosines. Let's prove the law of cosines. This is a simple elementary thing. Supposing we have 2 vectors, A and B, and we want, think of it as 2 sides of a triangle, and we want to compute the length of the other side of the triangle. So let's call that C. C is equal to A plus B. How do we compute the length of C? That's just C is equal to A plus B squared, or A plus B dotted with A plus B. The square of the length of a vector is the dot product of the vector with itself. So if the vector happens to be C, this is C dot C, that's the square of the length of C. Did I make a mistake? Sorry, A minus B, thank you. A minus B. C is A minus B, it's not A plus B. A plus B would be over here. We could do it that way, couldn't we? But let's do it, it's A minus B. And you can work out very quickly that this is A minus B, do it yourself. Okay, so it's A minus B squared. What is this equal to? This is equal to A dot A plus B dot B minus 2 A dot B. Right? Just multiplying them together. And this is just the square of A. This is A magnitude of A squared plus the magnitude of B squared. And this is minus twice the magnitude of A times the magnitude of B times cosine of the angle between them. That's called the law of cosines, that the size of the third leg of a triangle is given by the sums of the squares minus twice the product of the lengths times the cosine of the angle between them. Okay, so that's vector addition, vector multiplication, vector subtraction, even vector multiplication, the dot product. We'll worry about the cross product another time, not today. All right, now, not more important, but more interestingly, we have not only a algebra of vectors, which means adding, subtracting, and so forth. Oh, as I said, there's no notion of division of two vectors. And notice that for the dot product, the product of two vectors is not a vector. It's a number. The cross product is another matter that we'll come to another time. Okay, now, let's talk first of all about a particular vector which characterizes the position of a particle. Here's the position of a particle. Now think of it as a particle. In fact, we're going to allow it to move around in a little while. And the origin is a particular special point that we've picked out. We do have to worry about what happens if we change the origin, but we're not going to do that today. And therefore, the position of the particle defines a vector. That vector is usually called little r. R, I suppose, stands for radius. And in fact, the magnitude of the vector r is the radial distance from the origin to the particle. That is true. R, presumably, I don't know where the notation came from. I think it was for radius. But for now, it stands for the position of the particle. What are the components of r? They're just the x, y, and z of the particle. They're just the coordinates of the particle, x, y, and z. So r has coordinates x, y, and z, or let me not write it that way. R sub x is equal to x, the position x, and so forth and so on. That's the notion, the simple notion of the location of a particle described as a vector. Now, in general, we are interested in the motion of particles. The motion of particles is what classical mechanics is about. How the motion goes from one instant to the next, in other words, how it's updated from one instant to the next. And so we should think about r as a function of time in general. It moves around. However it moves around, we'll assume it moves around continuously, differentiably, smoothly. And at the same time, its components. If r is a function of time, then r sub x is also a function of time. Likewise for y, y of t, and z of t. And so the motion of a particle is summarized, in this case, by three functions of time, x, y, and z. What about the velocity of a particle? The velocity of a particle is also a vector. It has a direction. It's not necessarily the direction of the position of the particle from the origin. For example, the particle might be over here, but moving this way, moving out of the blackboard. In that case, its velocity would be this way, but its position would be this way. And so they're two separate, distinct vectors. The position could be any vector, and the velocity any other vector. But how do we describe the velocity? The velocity is the time derivative of the position. All right, I'm not going to spend a lot of time explaining that fact. I think you all probably know. If not, you're probably in a little over your heads. But I will assume you know this, that the velocity of a particle is the time derivative of the position of the particle. So we can write that in a number of ways. We can, first of all, say that the components of the velocity along the x-axis is the derivative with respect to time of the position of the x component of the position, or we can write it either as r sub x, or we can just write it as dx dt. And likewise for the other two components of velocity. So the velocity is also a thing with three components. It's also a thing with a length, the magnitude of the velocity, which is called the speed, the magnitude of the velocity, and it has a direction. And the components of velocity are just the derivatives of the components of the position. So there's a velocity vector, And it's easiest to specify by specifying its components. The x, well, I won't write equals. It has components x, y, and z, which are the x dt, the y dt, and the comma, and the z dt. That's the notion of the velocity vector. And I will frequently and almost always use a notation which many of you know, but I will introduce it here anyway. Differentiating anything with respect to time, calculating its rate of change as time proceeds. There's a traditional notation for it. Some of you know it, some of you don't. I'll tell you right now. The derivative of anything, let's call it any function of time, with respect to time, is just labeled, this is just in order to keep from having to write d by dt over and over, is just to put a little dot on top of it. Dot. Definition of a dot on top of a function is its derivative with respect to time. It doesn't mean the general, you wouldn't use it for derivatives with respect to space, you wouldn't use it for derivatives with respect to anything else. Dot means derivative with respect to time. Okay? So we could rewrite this saying that the components of velocity let's write it in one formula, v sub I, where I could be x, y, or z, is equal, first of all, to dx sub I by dt, which is the same as x sub I dot. That's the notation for velocity. Velocities are important. Let's work out an example. Well, no, before we work out an example, let's talk about acceleration. What is acceleration? It's the rate at which the velocity is changing. Acceleration is 0 if velocity is not changing. Whenever the velocity changes, there's acceleration. Acceleration is also a vector. It's not just 30 miles an hour per hour, or 30 feet per second. It's also got a direction. A thing can accelerate that way, it can accelerate that way. If an object is moving slowly along the plus, so that's your plus x-axis. If it's moving that way slowly and then it speeds up, you would say the x component of acceleration is positive. If it's moving fast and it slows down, we would ordinarily call that deceleration, but mathematically it's negative acceleration, which means that the x component of the acceleration is negative. It could be exactly the same acceleration as if you started from rest and accelerated along the x-axis. In both cases, a change of the velocity along the x-axis is called acceleration, and it's simply the time derivative of the velocity. All right, so we write acceleration, the components of acceleration are the derivatives of the velocity with respect to time, or we could write it as v dot, of course, v dot I. But that makes it the second derivative with respect to time of the position. The second derivative is usually labeled with 2 dots on top of it. 2 dots means second derivative. 1 dot means first derivative. No dots mean don't differentiate it at all. 3 dots means a third time derivative, and so forth. So acceleration is the second time derivative of position with respect, well, second time derivative of position, period. We could also write this in vector form. We could write that the velocity as a vector is equal to the time derivative of the time derivative of the position vector, or just, this gets a little annoying, r dot. R with an arrow to indicate it's a vector, dot to indicate the time derivative. Likewise, acceleration. Acceleration is the second derivative, r double dot. Okay, now that we have these concepts, let's work out an example or two. Two specific examples of position, velocity, and acceleration. Okay. How are we doing? Okay. First example, motion along a line. Particle has a position x. This is the x-axis. A particle is labeled as having a position x of t. Along one axis, it's hardly worth thinking of it as a vector. We just think of it as x of t. It is a one-dimensional vector, but one-dimensional vectors are too trivial to even call vectors. Just x of t. And let's, as an example, let's write down a particular formula for x of t. This is x of t, which we're going to assume is a constant, some number, plus b times t plus c times t squared. Now, there's nothing to prevent us from going on, but let's suppose that is the formula which tells us where the particle is at any given time. Right? In particular, at the start, let's take the start to be at t equals 0. At t equals 0, the particle is at a. Okay. Let's calculate the velocity and the acceleration. You all know how to do this. To calculate the velocity, we write x dot, and that's the first time derivative. The derivative of a is 0. It's just a constant. The derivative of b times t, b. And the derivative of ct squared, plus 2ct, right? All right, so this tells us now that the velocity at time 0 is b, right, to start with. But then the velocity starts increasing. Of course, it depends on whether c is positive or negative, or whether it increases one way or the other. But whatever it is, it starts at b, and then as time goes on, it either increases or decreases depending on c, linearly with time. What about the acceleration? We just differentiate again. What's the derivative of b? And the derivative of 2ct? 2c. Okay, so this is the acceleration. It's twice c. It's constant with time. It's constant with time. It doesn't change. So this is a uniformly accelerated particle. Okay? That's a uniformly accelerated particle that has acceleration 2c. That's the kind of motion you have of an object falling in a gravitational field with a constant acceleration, but here it is, and here's the reason why. What I want to do before we finish is one more example, which is more interesting, and it's circular motion. Motion in a circle. This will teach us something interesting and new. Let's think of a particle moving around in a circle. It starts at time t equals 0 along the x-axis. So here's x, and here is y. X and y are the components of its position. For us now, we're going to ignore the third direction. Z plays no role. It's a particle moving on a plane. It has two coordinates, x and y. And at any given time, it's on the circle. The angle increases linearly. The angle just continues to increase and increase. Of course, when it goes all the ways around, the angle goes from 2 pi back to 0. But we don't have to say 0. We can keep letting it go, wind up higher and higher. The angle is that. So here's the angle theta. And the angle increases with time according to the rule theta is equal to some constant called omega times t. It's not a w, it's an omega, a Greek letter omega. How long does it take to go all the ways around the circle? Well, to answer that, we just say how long does it take for it to go from theta equals 0 to theta equals 2 pi? 2 pi is 360 degrees in radians. We're working in radians, of course. So we simply solve the equation. 2 pi is equal to omega times t, or 2 pi omega is the amount of time that it takes to go all the ways around, and that's called the period. The period of the motion is 2 pi over omega. And that, of course, determines what omega is. If we know the period, we solve this equation for omega. If we want a particle that moves around in a circle in 1/10 of a second, we put in for the period 1/10 of a second, and we calculate omega. All right, so that's what omega is. It's called the angular frequency. But let's now consider what are the x components and what are the x and the y components of the position of the particle. And that's easy. Let's have it moving around on the unit circle for simplicity. Let's have it moving around on the unit circle, which means radius equal to 1. Okay, what is the x component of the position? Cosine theta, right? Cosine theta. What is the y component? Sine theta. Okay, so now we know the components of position as functions of time. X of t is equal to cosine of omega t. Y of t is equal to sine of omega t. And now we can start calculating the velocity and the acceleration. All right, so let's calculate the velocity and the acceleration. I assume that you know how to differentiate a function like cosine omega t. All right. So we just have to compute the first time derivative to calculate v sub x. And the time derivative of cosine omega t is what? Okay. Minus omega times the sine of omega t. Okay, everybody know that? Anybody not know that? In the notes, I suspect there's a whole primer on calculus. And one of the things that I think is discussed is derivatives of trigonometric functions. So to differentiate cosine, the derivative of cosine is minus the sine, but because of the omega here, there's an omega here. So this much I expect that you will be able to, either you know, you recognize it, or you'll be able to go home and figure out why this is true. What about v sub y? Omega times cosine omega t. Okay, now I have an interesting question for you. What's the angle between the velocity and the position? The position is over here. What's the angle between the position and the velocity? It's pretty obvious that it's 90 degrees. You can see that just by saying, well, we know the velocity is going to be moving along there. But how can we check it? We can check it by checking the dot product. Here's x and y are the components of a unit vector. Vx, vy are the components of the velocity vector. What's the dot product between the position vector, let's call it r, and the velocity vector v? Well, it's the product of the x component of position times the x component of the velocity, plus the product of the y component of position and y components of velocity. So it's cosine omega t times minus sine omega t plus sine omega t times cosine omega t. They cancel. This product here has a minus sign in front of it. This product here has no sign. Both of them have cosine times sine in them. So there's a direct calculation of the dot product of position and velocity, and it's 0. What does it tell you that the dot product of two vectors is 0? It tells you that they're perpendicular. Okay? So without, intuitively it's obvious that the velocity and position are perpendicular to each other, but here's the calculation that proves it. Okay. Let's go another step and calculate the acceleration. The acceleration is another derivative. All right, so what's the derivative of minus omega sine omega t? Well, it's minus omega times the derivative of the sine, which is another factor of omega and a cosine. So this would give us minus omega squared cosine omega t. And what about a sub y? Derivative of omega, we first of all have a factor of 2 factors of omega. And the derivative of cosine, this is equal, minus sine. Well, let's compare A with the position itself. The position is the vector cosine sine. The acceleration is minus omega squared times the same vector. Okay. So apart from, the omega squared is important. It tells us how fast the velocity is. But what's important here, apart from the omega squared, is the fact that A lies in the same direction as r itself, except not quite. It lies in the opposite direction. There's a minus sign here. So that tells us that when the particle is over here, its acceleration, r is pointing outward, the acceleration is pointing inward. The acceleration is pointing inward toward the origin. We all know that the acceleration of a particle moving in a circle is toward the origin. It's a centrifugal acceleration. But here's the mathematics that demonstrates it, that the velocity is perpendicular to the position of the particle, and the acceleration is parallel but in the opposite direction. How about the magnitude? The magnitude of the position is 1. I put it on the unit circle. What about the magnitude of the velocity? Velocity. It's just omega, right? Just this, the x squared plus vy squared is equal to the square of the magnitude. Sine squared plus cosine squared equal add to 1. So we're just left with omega squared for the square of the velocity. The velocity of this particle is just omega. Now that makes sense. The larger omega is, the faster this thing circles around here. And in fact, the velocity is just proportional to omega. How about the acceleration, the magnitude of the acceleration? It's omega squared. Okay? So the bigger omega is, the bigger the velocity, but even more so for the acceleration, but acceleration opposite to the direction of the position of the particle. All right, I think that's all we wanted to do for today. We've covered some material. I wanted to go through the simple elements of acceleration, velocity, circular motion, motion on a line, and the next time we'll start to talk about what are the initial conditions for a particle, what is the space of initial conditions, and what are the laws of motion? What are the things which tell us how the particle moves from one instant of time to the next?